Hello and welcome to Better Man Brief. My name is James. Today we're talking about the power grid part 3. In the first two parts, we talked both about power generation in part 1 and then how that power made it to your house and a little bit on what happens with blackouts, brownouts. So if you're interested in that, watch that video. And then in part 2, we briefly talked about battery storage or energy storage and how that plays into the power grid. And that's in video part 2 if you're interested in that one. And then today, part 3, we're going to be talking about how electricity moves along the power grid. In particular, we'll be touching on 3-phase electricity, the single phase as well as the 2-phase that you find in your house. We'll wrap all of that up with a little bit about how the transformers kind of work. Without further ado, electricity is transferred around the wire rather than how we normally think of. We normally think of power line poles being more like a plumbing system where water travels through the pipe. When it comes to power lines, the electricity actually goes around the wire rather than through the wire. So you have a bunch of little wires that allows lots of electrons to orbit around them, creating that magnetic field. And then in an AC system, which is an alternating current system, you have an oscillation of power. So you don't get a single flow directionally of electricity, how you do with a battery system where it goes from the positive all the way to the negative and then it terminates. And alternating current, you have it going one direction, stopping, going back the other direction, and then going back and forth continuously. In the US, we have a 60 hertz system, which means it oscillates 60 times per second. One way to think about that is if you have a chainsaw, the chain goes one direction as you're trying to cut down the tree, and it's always moving one direction. That'd be your DC or direct current as it's wrapping around the blade, so it's always cutting from the same angle. It's going to cut down the tree, but it's going one direction. The alternating current is more like a two-person fixed saw, more that you saw like back in the early 1900s. I don't know when that blade was actually invented, but where it goes back and forth, two guys pushing and then pulling. One guy pushes, the other guy pulls, and then they reverse. So that back and forth motion will also cut down the tree. It's just a different method of applying energy into cutting the tree. So the way you look at AC is that back and forth motion that constantly goes on the lines. And that's what we normally get power in our houses. And then in certain systems, we have the DC current. In our house, we have 120, but you'll notice certain devices in the house operate on 240. And what that is, it's just taking two hot lines. So your dryer or your electric stove, oven, those both run on 240, and you're just taking two hot lines and they're both 180 degrees out of sync with each other, and then connecting them to the dryer. When one is at peak positive, one hot line, which is 120, the other hot line, which is also 120, is at peak negative. And so the difference between them is 240. So the way to think about that is if it's me and another guy and we're each one of the hot lines, when I'm pushed all the way out, he's pulled all the way in for that saw motion on the tree, and then vice versa. Then as I'm coming back, I pull all the way in and he pushes all the way out. So it gives us that full range of motion. And what that full range of motion is 240 volts. So that's what that home system operates on, is that 240, giving you a lot more work that can be done on that system. Only appliances that need a lot more work to get done, generating lots of heat, requires lots of work. So those are the ones that you put on the 240 system. Because they're working together like that, you can actually run the hot from one through the hot the other and treat one hot line as the neutral for the other, or the return, because they're in opposite sync. The neutral becomes like a ground in that case because of how that power system is set up and operates. So now I already briefly mentioned a tri-phase. So if the dual phase is 180 degrees off of each other, you might be wondering, how does tri-phase work? Tri-phase is 120 degrees off. So think about it, if it's a circle, it's a little pie chart, and each has its little third section off. So you got 120 and then 240 and then 360, and that way they each are a little bit off. What that does is it increases the amount of work that can be done, because you got three hot lines and they're all working off sync with each other to increase the amount of work, but it also smooths out that, so you don't have these like sharp peaks. Whereas in a single phase, you're gonna have work being done, not being done, work being done, not being done, is the way to think about that. Dual phase, you get work being done one direction, then you get work being done the other direction, but you can think almost there's a gap in between. That saw motion may not be the best example in that case. So with the tri-phase, what you're getting is a peak. You can almost think about it maybe at this point like an engine with the pistons going up and down when each one is firing at its peak point. So with the tri-phase, you're getting those peak points spread out a little more evenly, which gives more steady flow of power and smooths it out. It's really good when you're working with precision machines if you're wanting a smoother network. So tri-phase you don't find in the home as much as you'll find in factories and any other large industrial setup that requires a lot of power and also wants a little bit smoother delivery. So that's what you're going to find with that. Also, tri-phase is more efficient. The electric motors that run on tri-phase don't require as much in them. They don't need a capacitor to get them started. And all a capacitor really is, I can talk about that more in another video, but just briefly, a capacitor is kind of like a battery. You can think about it like a battery, but stores way less power, but can eject all the power much quicker. An example of little capacitors that you would find is like in cameras, especially old cameras where you could hear the whine as the capacitor was charged up, and then the discharge would be rapid with the flash. So it's releasing all its power at once, and you get a big bright flash. The camera opens its shutter, and you get the nice bright white light. And that's way more power than the battery can discharge all at once. So thus the battery charges the capacitor, and then the capacitor can then release all the power as needed. So that's all the capacitor is there. It's just when you flip on like your fan, ceiling fan, it just needs a little bit of power to get it rotating at the start. So the little capacitor can give it that charge. Actually, I don't know if fans need that, but that's what would utilize it in a single phase. All right, moving down. We're talking a little bit about transformers now, just to give you an idea of why we have those transformer stations set up. So all those stations do is you'll have power production happening. It hits a transformer station. Transformer station converts the energy into a high volt, low current state. That allows it to transfer longer distances without losing as much power. And then on the other end, you have another transformer station that takes the high volt, low current and converts it down into lower volt, higher current state, because our house is like lower volts, higher current. And then we'll have our own smaller sub transformer, like the little ones that you'll see on power line poles, just those little gray cylinder ones, unless they're buried in the ground. Those are just stepping it down again to give you that nice 120. And the way you can think about that, why that's working that way, is think about it like in a car going down the interstate. You want to be in the highest gear possible because you're going to get the furthest distance on the least amount of fuel. But when you get to your destination, if you're a big truck or a tractor or some heavy machinery, you're going to want to go into a lower gear to get more work done. It's not as fuel efficient for long distance travel, but when it comes to doing the work at the location, that's where you're going to get all the power that you need to get the job done. Similarly, you're stepping the volts back down, raising the current so that the work that you need to get done can get done in the location, being our house, doing whatever it is. When it's just getting point A to point B, you want the highest volt possible, least current, because it's not trying to do work between those two destinations. You're just getting it from point A to point B. So it's just like going down the expressway. You want to be in top gear. Top gear doesn't allow you to pull as much weight or do as much work, but it's much more fuel efficient for traveling the distance for that vehicle, that speed. So that'd be the way I'd say to think about that portion of it. It's just like driving in sixth gear, but then when it actually comes time to do work, you want to go down to first gear, but you got to downshift. And that's what those transformers are doing. They're taking the power and downshifting it. It's actually really cool because the way the electricity is traveling, the electrons are creating that magnetic field around the power lines. Transformers just run like a loop and it doesn't actually connect to another one. It's that magnetic field that the power line's generating then gets transferred over. And you got the smaller transformer that's going to pull the power down for your house, and that as the electricity, the magnetic field is created from one, it generates magnetic field on the other, which is the electricity then traveling on the line. So that's how you get that step down process inside the transformers. Brief overview. We can go into more depth about how all that works. If you're interested, just leave a comment below saying that's something you'd be interested in knowing more about, and I'll create a video on that. Otherwise, moving on to the last part for the ground and neutral. So if we've got all this power working the way it does, what does the ground and neutral actually do? Remember, we're talking about 3-phase and 2-phase. Single phase, which is what you have in most of your house outlets, that's the single phase, right? That's just the 120 volts. So that one needs a place for the power to go. It needs the direction because it doesn't have the opposite pull. But going back to that saw analogy, think about it as a single person saw. So you got the handle on one side, no handle on the other side. So then you're doing the push and the pull by yourself and no one's on the other side to push or pull. And the way you think about it is if you got a wall on the other side, you can't push if there's a wall there. So you need somewhere for it to go. And then obviously you're pulling back. So as you go back and forth, you need that space. That's pretty much what the neutral is doing for you. It's allowing the power to go back down the neutral line for any of the unbalanced loads. Now the ground is there as a safety because the power wants to return to its source. So in the case of your house, your power source is that transformer box that's on the power line pole or in the ground somewhere. And you'll see on those, they'll have a little ground line running down to the ground. And then your house similarly in the electrical box has a ground line somewhere going down to the ground. And that way then, if for whatever reason something happens, doesn't make it back to a neutral, you can always ground it and it'll make it back to the transformer via a different route. Hopefully you're not the one that's standing in between the hot and the ground, because then that's when it travels through you to get back. It doesn't like to go through the ground. Ground is not really good about conducting electricity, but it's better than nothing. So that's what's making that final safety connection. And then hopefully you're not the one that's standing in between the 2 points on that. Generally, if everything's wired up correctly and there's no faults in your electrical system, you should be safe to touch the ground line, but it's also just good practice not to do that. All right, that covers all of the topics I was wanting to talk about in this video. If you found this interesting, please leave comments, especially on future topics that you're interested in hearing more about. With that, taking the electron side of this, I'm going to branch a little bit more into the periodic table. So if you're interested in that, subscribe. That'll be the next video coming up. Otherwise, this is Better Man in Brief. I hope you enjoyed it and have a great day.